Okay, so the next question is easier. So this time, let's say this is exercise 5 now. So here in this question, we are going to have the numbers from 1, 2, 3 up to 100 that we can select. And then altogether, we are going to select 51 numbers. And then we want to show that no matter how you select these 51 numbers, so let's say the numbers that you select, let's call it S1, S2, S51, then you are going to always to find some Si and Sj such that Si divides Sj properly. Okay, so from 100 numbers, you are going to select 51 numbers. And then no matter how you select these 51 numbers, you are always able to find two numbers such that one divides the other. Now this is also a tight result. Okay, so why is it tight? Is it tight? Let me see. Yeah, this is a tight result. So for instance, if I change it to 50, then there is no guarantee. Reason, I choose the 50 numbers as 51, 52, 53 up to 100. So I got the larger half of these 100 numbers. Then in that case, no two numbers you can find such that one divides the other, right? But on the other hand, if you just add one more, 51, it always guarantees. Okay? Now the proof of this one is by greedy selection. Okay. So we are going to distribute. So we are going to distribute somehow, because we are going to use pigeonhole principle. So we are going to create 50 boxes. You will see. So we are going to create some boxes. How many? Let us decide later. But you will see that there will be 50 in total. That's what we are going to select. Okay. Now, so what is the purpose of these boxes? So we want to show that, okay, whenever so we are going to put the numbers here in the boxes, such that if two numbers are in the same box, then one divides the other. Is that okay? So this is the criteria. So inside each box, if there are two numbers, then we are happy. We will find two numbers such that one divides the other. Okay? Now, we are going to distribute the numbers in the box in such a way that each number belongs to exactly one box. Okay? So, for instance, 1 will belong to this box. Because there is one box containing 1. Let's call it 1. Okay? Now, let's see how we should divide. Okay, so how about 2? So where should we put 2? Okay, we can put 2 in a new box, right? But it is better to put 2 here, more greedily here, in this box. Because if 1 and 2 are selected, then 1 will be in this box, 2 will be in this box, and then these two numbers, one divides the other, then this will be great. So greedily, we put 2 here. Okay? How about 3? So for 3, then we should not put it here, because let's say if 3 and 2 are selected, we are looking at 2 and 3, then 2 and 3 are in this box, but then 2 does not divide 3, so it is not good. So for 3, let us start a new box to store 3. Is that okay? How about 4? Can I put 4 here? Can I put 4 here? Yes, I can put 4 here. Whether I'm selecting 1, 2, 2, 4, 1, 4, it's okay. Any two numbers, one divides the other. Is that okay? 5, I cannot put 5 here because I may be choosing 2, 5. I should not put 5 here because I may be choosing 3, 5. So for 5, I'm going to put here. Is that okay? 6, how about 6? Where should I put 6? Could I put it here? No, because I could be selecting 4, 6. Okay, so this does not fit my choice. So 6? Yes, so 3 and 6. 7, so where is 7? Cannot put 7 here, no 7 here, no 7 here. Okay, so we start a new box for 7. And how about 8? 8 here. Okay. 9, how about 9? 9, can I put it here? No, 6, 9 is not okay. No 9, no 9, so I should put 9 here. How about 10? 10 cannot be put here, 10 cannot be put here. Okay, 10 can be put here, so I get 10 here. So what is the pattern? So let's see. So this is 1, 2, 4, 8. What is the next number that I will be putting here? 16. Good. How about this one? 3, 6. What is the next number I'm putting in? 12. It's 12. And after 12, what is that? 24. 5, 10. Next one? 20. 7, 14. Next one? 28. Okay. What is the pattern? The pattern here is that each number belongs to the bucket when you remove all the 2 factors. So let's call it bucket 1. Let's call it bucket 3. So we will have a bucket for each odd number. Bucket 5, bucket 7, bucket 9. So 9, you will have 18 here, and so on and so forth. And in the end, I will have a bucket 97, and I will have a bucket 99. So 97, I put 97 here. 99, I put 99 here. Is that okay? Is that okay? Each number belongs to the bucket. So each number, you can write it as a bunch of 2 multiplying with an odd number. Okay, so if I have a number 48, so 48, I will be putting it into bucket 3. Is that okay? So I take out all the 2 factors and see what is the odd number remaining. Okay. Now, what's so special about this one? There are exactly 50 boxes. There are exactly 50 boxes. If I'm selecting 51 numbers, then what does it mean? So if I'm selecting 51 numbers, then maybe I'm selecting 3. Then it's like I put a ball in this box. I'm selecting 7. I put a ball in this box. I'm selecting 18. I put a ball in this box, right? So I'm going to throw 51 balls into 50 boxes. Then one of the box contains 2 balls. One of the box contains 2 or more balls, actually. Then inside this box, we have selected 2 numbers, such that one divides the other. Is that okay? Okay? Okay. Well, not easy, but not as difficult as the previous example. Okay? Okay. Now, let's do one more example. Okay. Okay, the next example is going to be hard, so I will have a warm-up exercise for you. So let's write down how many numbers? Let's write down 7 numbers. Okay, whatever 7 numbers that we like, maybe 4 integers. Let's say 4, 6, 1. Well, maybe not 1, 2. Let's say 2. It can repeat. Okay, you can have a 2 again. 5, 5. No, not 5. Let's do it 6 again. And then let's say a 3 here. 1, 2, 3, 4, 5, 6. We have one more. Let's get a 5. 5? No. Let's get a 4 here. Whatever. Okay. Okay. 4 here. So we want to show that there exists a contiguous subsequence. So we have defined subsequence, right? Subsequence. So 6, 2, 3 is a subsequence. Okay. but then you have empty space, not selected. So if your subsequence turns out to be selecting numbers that are together, then we call it contiguous subsequence. Contiguous subsequence, okay. So we want to show that for any 7 numbers that you select, 7 integers that you select, there exists a contiguous subsequence such that the sum is a multiple of 7. Okay, let's see. Is there some? So yeah, for this one, 4 plus 6 plus 2 plus 2 is 14, so it is a multiple of 7. Okay, yeah, maybe you don't like this, then let's make it 3. Let's see if we can get something different. Well, then what do we have? Let's see. 5. Oh, okay, then in that case, this is 11, right? This is 14, right? Right? 14. Yeah, maybe you don't want to have a 14 here. So let's have a 5 here. Let's this time have a 5 here. Oh, but then this one, this is 14. Okay. Maybe you don't like. So let's make it 3 again. Okay. Then do we still have multiple of 7? Let's try. 8, 5, 13. Do we still have multiple of 7? 5, 5, 3. Let's see. Rather difficult. 6, 2, 3, 3. Let's see. Okay, 6, 2, 3. Yes, that's it. Okay. Yeah. No matter how we add it, no matter how we change, then we always find a subsequence, contiguous subsequence, which is divisible by 7. So why? Why is it true? Okay. It's very simple. Simple idea. So let's call this number A1, A2, A3, A4, A5, A6, A7. Is that okay? It's A7. Okay. We consider something called prefix sum. So what is prefix sum? So A1 is a prefix. A1, A2, these 2 numbers is a prefix. So we have another thing called A1 plus A2. So this is another sum that we are going to look at. So we have A1 plus A2 plus A3. Is that okay? So this is another sum that we are going to look at. And then we have A1 plus A2 plus A3 plus A4. This is another sum. Okay, A1 plus A2 plus A3 plus A4 plus A5. This is another sum. So altogether, there are going to be 7 sums. Is that okay? So let's don't be lazy. Let's write them all down. A6, okay. And then we have one more. A1 plus A2 plus dot 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 up to A7. Okay? Okay. Now, if any one of these sums is divisible by 7, then what do we have? We have a subsequence, actually a prefix, which is a multiple of 7. Is that okay? Okay? So the other case is that all of these are not multiple of 7. All of them are not multiple of 7. Then when you divide them by 7, then they will have different remainders. But then 2 of them will have the same remainder. Okay, if this one, let's say, and this one has the same remainder, then that means that the difference will be a multiple of 7. So in that case, you get the subsequence, which is a multiple of 7. Is that okay? So let's confirm our finding. So A1 turns out to be, let's look at the things when you look at them by remainder by 7. So A1 is 4. If you divide by 7, the remainder is 4. Is that okay? And then A2, if you divide it by 7, A1 plus A2, if you divide it by 7, the remainder is going to be 3. Is that okay? A1, A2, A3, the remainder is going to be 5. Is that okay? A1, A2, A3, A4, if you add them up, the remainder is going to be 1. Is that okay? And then if you add up to 5, the remainder is going to be 4. If you get 6, the remainder is going to be 2. And then if you add everything up to the last number, the remainder is going to be 6. Is that okay? So all of them are not divisible by 7. So no prefix is actually divisible by 7. But if you look at them, so you have 1, 2, 3, 4, 5, 6. Okay, but then these 4 and these 4 are the same. So that means that if you add everything from this one up to this point and everything up to this point, they have the same remainder. So in that case, the remaining part, the different, no, A5, sorry, A5. Yes. So that means that the remaining part, this is the remaining part. If you add them all up, this will be a multiple of 7. Is that okay? Oh, that's lucky. Yeah, we found this. Okay? Good. Okay? And actually, this seems to be the only subsequence that is a multiple of 7. Yeah, it is true. Okay? Yeah, because if there is a subsequence which is a multiple of 7, then you add this one, the prefix remainder will be the same as the prefix remainder here. You need to find 2 prefix remainder. That is the same. And this is the only case. You have 4, 4 here. Well, so lucky that we found this, okay? Before we use this technique. Okay. Now, so usually to make, so this is called the prefix sum, and it is usually very useful to prove examples of pigeonhole principles in this form. And usually, for convenience, we give it a name. Okay, so this is a prefix sum with just one number, so I will call it S1. This is S2. This is S3. Is that okay? And similarly, this is going to be S4, the sum of the first 4 numbers, S5, sum of the first 5, S6, and then this is going to be S7. Okay? Is that okay? Now, so the real challenge. This is the real challenge. So in this question, we are asked, so let's say we have a sequence of 30 numbers. So we have a sequence of 30 numbers. Let's call it A1, A2, A30. Okay, all of them, all of these AI, they are integers. They are integers. And then let's say, for each AI, it is an integer greater than or equal to 1. Okay? And then, fact, we also know that S30, which is the sum of every number, so which is the sum of every numbers, A2 plus ... up to A30, we know that this is exactly equal to 45. Okay? And then question here is that show that there exists a contiguous subsequence whose sum is exactly 14. Okay. Amazing. Okay, so these numbers, they do seem that they are unrelated. But notice that some of the conditions here are important. Here, this greater than or equal to 1 is important. So if AI could be 0, then what will happen? Then you may have just A1 is equal to 45, and all the remaining is 0. Then you don't find any contiguous subsequence whose sum is exactly 14. Okay, so this condition we need to keep. Is that okay? Is that okay? And similarly, maybe this 45 is also important. Okay? If this number, let's say this is like 100, or let's say this number is like Yeah, let's say this number is like 90 rather than 45. 90, let's say this is 90. Then what do we have? We may have all the A1, A2 up to A30, they are all 3. Then in that case, you don't have any subsequence whose sum is equal to 14. Does that make sense? So here, although this is implicitly important, this is also implicitly important. Okay? Also, 30 seems to be also important. If you just have 2 days rather than 30 days, then maybe the first two numbers, let's say A1 is 15, A2 is equal to 30. Well, 15, 30, you don't have any subsequence, adds up to 40. So somehow, these numbers are interrelated. Originally, this problem has a story. It is like there is a chess master who plays chess in April. April has 30 days. He practices the chess game at least once each day. And you know that in all the April, he has played exactly 45 games. So we want to show that there is a certain week, no, not week, there is a certain consecutive days such that the master has played exactly 14 games. Okay? Okay, but it is more easy to rephrase this as a problem like this. So actually, we have just 30 positive integers, and then they add up to exactly 45. And then we want to show that a subsequence of them adds up to exactly 14. Okay? Really difficult, yeah. Solution is easy. Everything that can be proven by pigeonhole principle is usually very easy. Once we know how to design the boxes and the balls, then it is easy. Now this is the solution. Let's see. So let us consider the numbers S1, S2, prefix sums, okay? S3 up to S30. So these are 30 numbers. Is that okay? So far so good, right? And then let's have another set of 30 numbers. The first one is 14. The next one is 14 plus S1. The next one is 14 plus S2 up to the last number is 14 plus S29. Yeah, perhaps it's better to write this as 29 and then S30 here. Is that okay? Okay. So why do I design these numbers? You will soon see. Okay, so altogether, how many numbers? There are 60 numbers that we have. Okay. What are the range of this number? The range of this number, the smallest number is S1, right? S1 is A1. A1 could be equal to 1. So the range is between 1. This is the smallest number. And what can be the largest number? Which one is the largest number? Maybe S30, maybe S29. It looks like S29 plus 14 is going to be the largest, right? S29 is less than or equal to 44. If you add, does that make sense? Right? So if you add 14, so the numbers are up to 58. Is that okay? Does that make sense? Is that okay? There are 60 numbers, and then they have the range from 1 to 58. So two numbers or more could be the same. Okay. There are two numbers which has to be the same. I don't know which two numbers, but I know one thing. If there are two numbers which are the same, one must be on the top part and one must be at the bottom part. Because in the same row, you cannot have numbers which is the same, because you add 1 for each new number. So S1 is strictly less than S2, S2 is strictly less than S3, and so on and so forth. So if I tell you that there are two numbers the same, then the two numbers must be one from the top and one from the bottom row. Is that okay? Good. So there are two numbers the same. Let's say these two numbers the same. So what do we have? So we have Si turns out to be equal to 14 plus Sj. Is that okay? Okay, we get it. So Si minus Sj is equal to 14. Is that okay? So what does that mean? So that means that Ai plus 1, no, minus Sj. So it is, J is shorter, right? So Aj plus 1 plus Aj plus 2 plus dot 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 up to Ai is exactly equal to 14. Is that okay? Is that okay? Good. So this problem works for what? If you know this, then you know that there must be consecutive days such that the chess master plays one game. There are consecutive days that the chess master plays 2 games, or exactly 3 games, exactly 4 games, exactly 5 games, up to exactly 15 games. Okay, 16 games, you may be able to prove that. It may be true. But then it's not just simple pigeonhole principle. But if you are proving that this sum, so whose sum is from 1 to 15, you can show that any of them is true. So there are consecutive days such that it is 1, consecutive days such that the total play is 2, and so on and so forth. Is that okay? Okay, so that's it. Okay. Okay, so that's all for the pigeonhole principle. Yeah. So don't worry. Okay, all the examples here that we have demonstrated are really hard examples. Just look at how beautiful that a simple theorem can bring us to this difficult theorem application. So in the exam or in your assignment, it won't be that hard, hopefully. Okay, so you find it out.